Welcome to UBC CS 532W 539 something or other, graduate probabilistic programming, another day, another lecture. It's going to be fun. I don't know what we could do to sort of increase the shared energy level. I think we all know that the energy level in last lecture was tragic. I would like to avoid that from happening this time. Maybe it would be helpful if I, didn't slander the various students in my comments, but I'll try to avoid that. But as more interactivity, more questions, whatever, I think is desirable. Anyway, so today we're going to talk about evaluation-based inference. Where are we? Well, we're still in FOPPL land, first order probabilistic programming land, and y'all have implemented an evaluator and graphical model and evaluation-based interpreter for FOPPL, and we've hit a couple of the inference techniques that one might implement, including Hamiltonian Monte Carlo last time. Hopefully you now understand a little bit about how Hamiltonian Monte Carlo works, and maybe having thought about it and started to implement it, you will get a sense, and at least enough of a sense that you could actually write such an engine for the FOPPL. Today we're going to do more evaluation-based inference strategies versus graph-based. Okay, and really the goal is to get you to think about an inference algorithm which is a little bit different to those which you have been assigned. Did I assign LMH? I did not assign LMH, right? Did I assign LMH, Brad? I don't think so. Lightweight Metropolis Hastings? No, I don't think so. Largely because I wanted to switch from doing that to black box variational inference, which is closer to modern and interesting state-of-the-art methods, although not all the way there. We'll get there in a later part of the course. So this, by the way, so in other words, in some sense, you can turn off and not pay attention to this if you want to, because there's no homework on it. But if you actually care about probabilistic programming, Lightweight Metropolis Hastings is a very powerful general purpose algorithm that was developed quite a long time ago. And yeah, okay, and is very general purpose and it's cool. So you should know about it. But really, the one that we'll talk about today, this is homework 4. Okay. So after homework 3, then you're going to do one more evaluator, thinking in a different style, and it's homework 4. You can just do all of them at the same time if you want to. I'm not going to give you a huge amount of time to do homework 4 because I really want to get to the point where we can be doing homework 5 and homework 6. But so, at least stay around to the end of the lecture so we can talk about black box variational inference, which you're going to need to know for homework 4. Okay, so just to remind, right, hopefully you're at the point where you're either done with this or nearly done with it, or understand what's going on. Clearly, if you have a graphical model, you can do graph-based importance sampling, where you topologically sort the link functions in your graphical model or in the data structure representation output from Daphne. And then for every random variable, latent random variable, you sample from the prior. For every observed variable, what you do is you compute a set of weights, right? Which is just to say you evaluate the probability of the likelihood under its link function. And that gives you an unnormalized weight or likelihood. And you return a set of weighted return values from the evaluating the program via its graphical model representation, where this XL is the collection of all of the latent variables that you sampled during your topologically sorted pass through the program. And the normalized weights, a la importance sampling, are computed for the L particles by normalizing the weights, by summing over all L particles, then assigning that weight to the atomic measure centered at the return value of the program, or in other words, the evaluation of the return expression of the program, given all the random variable values sampled in the traversal of the trace. And of course, WL, big WL is just the product of all of the intermediate weight computations that you do along the traversal of the graphical model, right? So this procedure, because we don't have an explicit proposal mechanism, we'll talk about that in a little while, how to change that. It samples in a prior, weights by the likelihood. This is known as likelihood weighting. It eagerly evaluates if branches, so it does extra unnecessary computation in some sense. We can forget about this for now, but this kind of this is very closely related to autoencoder style reasoning and the importance weighted autoencoder and these sorts of things. So are there any questions about this? Does everybody understand this should be really, really straightforward? I think we did this before already, right? This is a review. Okay. I'll take that as a total comprehension. Great. So the differences between graph and evaluation-based inference, I think we already know. There's no explicit representation of the conditional dependencies, right? So there's no graph whose structure can be exploited. It also is very different because we're going to lazily evaluate if branches. So in other words, we can have a different number of samples that are observed evaluated per trace. And a trace is just the sequence of computations that the probabilistic program takes during one execution path. And that will be a mix of deterministic computation and probabilistic computation, sample and observe. And obviously, we're going to care more about the sample and observe than we are about whatever, but your evaluator does both. I think we did the evaluation-based important sampling as well. Yes? Okay. So we have our standard evaluator, and the only difference when we're doing evaluation-based versus graph-based important sampling is that in the evaluation-based method, we have this evaluator, and we implement these two base cases such that when you sample, you evaluate the expression to get a distribution, you sample from the distribution, and then you continue. When you hit an observe, you evaluate the expressions recursively like usual, but then you affect the side, you affect a side effect, right? Which is to say you accumulate the log probability of the observed value here, C2, under the distribution arising from evaluating E1, D1, right? And the outer loop just basically keeps track of these the return values of the program and the log weights. Fine. Any questions about this? I will assume total comprehension on this one as well. And just because Barend is holding office hours and Christian hopefully will hold office hours if he does so as requested, does not mean that you should wait until then to ask those questions. Because I know that there is a distinct distinction between the questions being asked there and the questions being asked in lecture. So please ask if you have them. Is it just the point in the term? Did I like really just destroy the spirit of the class with the Hamiltonian Monte Carlo lectures, or is it just that this point in the term? Or I mean, it's not that bad of a day in Vancouver for those of us who are in Vancouver. Like, okay, all right, I'm going to assume total comprehension, and I'll yell at you if it's not true. Okay, I don't think we did this. So there are some. There is a relationship between evaluation and the inference rules we've been talking about. And I'll go through this very quickly. Again, you don't have to pay too much attention to this, I don't think. So inference rules formally specify how translation behaves, right? So in particular, we looked at program to graph, and they give a recipe for implementation. Well, there's an equivalent thing called big step semantics, which basically tells you how to run the program and produce a value as well. And it's a useful notation to have if you want to, prove things about languages and their and the kinds of values that can be generated in those languages. So the big step. Yeah.
Can I ask a question on the last slide?
Yep.
And this is the most basic of questions. I seem to have forgotten what it would mean by like inference rules. So could you remind me, please?
These horrible inference rules that have this notation, which is like the most gross notation ever, but the inference rules that allow you to infer that if these conditions hold, this.
Okay.
If this, then you can infer this.
Okay.
Okay, so these are the inference rules. Thanks. Yeah. So if we can go through this really quickly. Actually, hopefully, if you've actually read the inference rules before, yeah. So let's do a couple of these, and you'll get the flavor right away. I don't know which one to start with. So we have some evaluation context like usual. This is going to be a set of procedures. This is going to be a set of bindings. And this is going to be an expression. Evaluates to under the big step semantics. This is going to be the return, right? So remember, we go this way, right? So there are no preconditions. If you're in this translation context, then the expression C gets translated to, now these are going to be slightly confusing values, right? So this is going to be the value of C rather than the expression C now. Here, when we have a variable, we look up in the context its bound value. So if this is true, then this expression in this evaluation context evaluates to the value of the variable. Okay, fine. So how do we put things in our set of bindings? Well, if we encounter a let expression with some variable named v1, some expression e1, some expression e0, then what happens? Well, we evaluate e1, and that gets translated, because now everything is going to get turned into a value. It gets turned into some constant value plus some set of bindings. Right? Cool. Then we evaluate E0, the body, in an evaluation context which extends the set of bindings with a binding which binds the variable v1 to the value c1. And that's going to return a constant plus some likelihood term, right? So I should say this is not a binding, this is a likelihood term. Right? And cool. The return of this is basically C0, the value of having evaluated E0 with the bound value V1, blah, 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 okay? Plus the sum of whatever likelihoods were generated when we evaluated E1 and whatever likelihoods we have encountered when we evaluated E0, okay? And yeah, let's see which else would be helpful. So we know the procedure for sample, it just samples from a distribution. So here's a case that we would hit. There's some likelihood. There's an expression E. We evaluate E down to some distribution, which is a value plus a likelihood. So there could actually be observed inside of E. Then we sample a value from the distribution, and the return value of this expression is some constant plus a likelihood. yeah, plus any likelihood that arose from evaluating the body E. Okay, so if we have an observe, not terribly surprisingly, we evaluate to a distribution, we evaluate to a constant value. They could generate some likelihoods because there could be observes in those program statements. We evaluate the probability of the return value of E2 under the distribution returned from evaluating E1. That gives us some likelihood, and the value of the expression observed E1, E2 is just the constant E2 plus the sum of all the likelihoods that you would have computed when evaluating E1 and E2 and this expression in total. Okay, is this starting to make sense? Can you read this? Is it okay? You see what's going on here?
Can I just confirm?
Yeah.
So, like taking, I don't know, we'll go bottom left.
Yeah.
Could you read it as like given like bottom left denominator, if top holds, return bottom right?
Yep.
Okay. Thanks.
Yep, that's exactly how you read it.
Minor question, Frank. In the variable case, shouldn't we also be returning a likelihood of 0?
You can. Yeah, sorry,
Okay.
You're right. There should be a 0 here, comma 0. Yeah. That's yes, that's good point. Note, I think this is a little note for Berend. So this is where like the specificity of these representations actually matter. So in the graph-based semantics, observed does not return the value of the observed variable. Just as a historical artifact, we've always fought about whether or not it's appropriate to do so. In the evaluation-based context, you can. And there's a subtle reason for why there's a difference between those two, and I'm not going to go into it here, and I can't even remember it. I'd have to reconstruct it. But notice that this observe actually returns the value of the observed expression, just as a little a little thing. And obviously, you know, primitive function application does what you would expect. It accumulates the likelihood of evaluating all of these things. Compound function evaluation does what you would expect. It binds all the variables to the formal parameters of f, and then evaluates the body of that expression of that user-defined procedure, and accumulates the likelihoods. And what's, I guess, the last thing that we should just point out, just to see how this is read, right? If we get to an if expression, and this is where the inference rules sort of come into play, and lazy rather than eager evaluation takes place, right? If you're in this context and the evaluation of E1 returns true, then you only actually evaluate E2. So the case control is covered by these two inference rules. One is if the predicate returns true. One if the predicate evaluates to false. Okay, lots of fun stuff. I tell you're super enthused by this, but it's good to have it in front of you so that you can read that stuff when you're in the book, which hopefully you're reading. Okay, so let's do evaluation-based inference. So we've got important sampling done. We've got a couple of different choices. I'm just going to say this. You've got HMC, but you could imagine doing Hamiltonian Monte Carlo where you only have the control flow path, right? This is okay, right? In other words, you're going to evaluate the gradient only where you are on the control flow path. And this will reduce to Hamiltonian Monte Carlo in the graph if there is no control flow. Okay, so Hamiltonian Monte Carlo with control flow is the same thing as Hamiltonian Monte Carlo with discrete random variables, and it's unclear what you should do when your gradient takes you to onto a different control flow path. And this is how you start to think about that. But we're going to talk about LMH, or random database, today, and then we're going to talk about a black box variational inference. We're going to postpone the other very important inference algorithm, sequential Monte Carlo, until we talk about the higher order probabilistic programming language for no particular reason. Okay, so how do we do evaluation-based Metropolis Hastings? So we talked about Metropolis Hastings. You know what Metropolis Hastings is. You know that you have some proposal distribution, and you evaluate the ratio of joint densities, and that gives you a sequence of posterior samples that in the limit converge to converge in probability to the stationary distribution of the chain, which is the posterior distribution, blah, 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 blah. Fine. So Metropolis Hastings methods generate an unweighted sequence of program return value samples, which are convergent in the sense we were talking about, the strong law of large numbers, via the strong law of large numbers, by accepting or rejecting a newly proposed sample according to the following pseudo algorithm. Okay, so we initialize the program state in some sort of a way. Anybody have a good way of initializing the program state into a valid state? You will encounter this when you start thinking about doing graph-based MH or graph-based sampling methods. You probably want to start the program off in a reasonable state. How would one do that?
Sample from the prior.
Sample from the prior, awesome. Where did that come from?
Adam.
Okay, great, yeah, okay, fine. And then for every subsequent sample, then we need to generate a proposal somehow, and we need to compute the ratio of the joint likelihood of now a trace, right? At the new y prime x prime points and at the old y x points, and then you have the Hastings ratio here of what's the probability of proposing x from x prime and x prime from x, where again x prime are the latent variables in the program. Okay, and you know how to use that acceptance ratio to decide whether or not to accept the sample. Okay.
Can I ask a quick question?
Yep.
It's not really related to this slide, but so like what we're working with currently are first order probabilistic programming. Like we're in FOPPL, the first order language.
Yeah.
Is it first order because like I guess I'm wondering what makes it first order.
So there's some fights about this even within my group, and we have made this terminology ourselves. So first order versus higher order usually refers to the fact that a higher order language will have functions as first class objects and unbounded recursion, and first order will mean that the language does not have those facilities. So very specifically, what we really mean, we could have called them graphical model probabilistic programming language, and then something else, not graphical model probabilistic programming language. But the point is that in the FOPPL, the number of random variables is determinable at compile time and is finite.
Okay. And so the higher order random variables can show up as needed in the program?
Technically, the number of random variables in the program is infinite in general.
Okay.
So another way of, in your head, what you should be thinking about is there's this funny thing, and it's very difficult to visualize or to even think about or whatever. There is this graphical model, right? And there's a bunch of ways of doing inference let's stay in FOPPL land. There's a bunch of ways of doing inference in the graphical model. One of which is to actually manipulate all the variables simultaneously. the other which is to evaluate the program and compute the joint probability of a particular configuration of the random variables. Now, of that particular trace. So it kind of makes sense in the important sampling case. It's really straightforward, right? You just run the program and you evaluate likelihoods. The fact that this corresponds to important sampling in the graphical model has to do with the way we designed the semantics in the first place. Equivalently, this if you really start thinking about what I'm about to go through, it's actually very amazing that these things both work and access the same probabilistic object or describe the same probabilistic object. Okay, and I think you're getting to the point where you'll see why that's kind of crazy. So basically, what I'm saying is we're going to be like the trace-based or evaluation-based inference methods, and this is how we get to the FOPPL thing, because the only methods that work in FOPPL land are evaluation-based inference methods. So by talking about evaluation-based inference methods now, even though the number of random variables is fixed and finite, all we're really thinking about is traces that will move across and between the control flow segments of the program. So in other words, they'll go down different control flow paths. And you can think about what we're about to see as basically a way of both moving within a control flow path and moving between control flow paths in a way that the ergodic averages work out correctly.
Okay. That made me think of another question. So when you say trace, I think matrix trace, and now I'm realizing that's probably not what you're talking about.
Totally 100% not what I'm talking about. A trace is a sequence of random variables. It is basically the sequence. A trace is when you do think evaluation-based importance sampling, there is going to be a sequence of there's going to be a sequence of computations performed. There's going to be a sequence of function applications done, right? You're going to do like, at the end of the day, the computation that gets done is what? This and this and that's it. There's a side effect that's computed here. So in other words, as you run the program, if you actually track what happens mathematically, there's a sequence of function applications and sample statements. That's it, right? And every time you run the program, you're going to get a different sequence you will certainly get a different set of sampled values. But because you get a different set of sampled values, that means that you may go down different control flow paths because you have different sampled values and different deterministic computations that are done on those that form the value of the guard of the if special form.
So it's like kind of the trail you take through evaluating.
That's 100% what it is. Yes.
Okay. Thanks.
Can I also quickly ask a question?
Yes, please. This is great. Good. Thank you. Yeah.
Yeah, it's not exactly related to what we are talking about right now, but
Please.
You mentioned that when we do Metropolis Hastings, for a continuous latent variable, we use normal as the proposal distribution, right?
No, I haven't talked at all about what the proposal distribution is, but this is good thinking because this is what you should be thinking about right now. So maybe I'll ask you, since I called you out positively before for your excellent code, hopefully you've been sharing it. Let me call you out, and let me call everybody out for a second, okay? We're going to do evaluation-based inference in just the FOPPL, right? What should that be? How do you do that?
I was gonna ask you that actually.
Yeah, but now I want you to think about it. Like, to everybody give a proposal for how one might choose or construct a proposal distribution.
If you pick some,
yeah. Go ahead.
I was just gonna say, I don't know if this is related to what we're talking about now, but before, when we were talking about this, if they're picked normally distributed, those terms cancel out. Sort of.
Yes, but no. So if you do this so we're talking about evaluation based, right? So we only have a trace, right? So proposing a, so let's think about, let me just say a couple of things out loud, and this will maybe make sense. If we're in graph-based inference land, you could imagine going into every random variable and changing all of the random variables in the program simultaneously via some proposal mechanism for each individual random variable.
What? I didn't understand.
Great. So we in the graph, in the graphical model, right? You have a big graphical model. A way to make a proposal, a joint proposal for the program state, would be to construct a factorized proposal where for every random variable, x1, x2, whatever, you propose, q of x1 given whatever, and you propose for all of them simultaneously.
What do you mean by simultaneously?
Like, you have to propose an entirely new joint state for all the random variables in the program. Baron, it looks like you're about to help save me, maybe.
To be honest, like, doesn't this end up being Gibbs sampling then, or if you, or
no,
or am I?
No, so that this is the whole point, right? So you can do Gibbs sampling, but that means you're only updating one variable at a time. But here I'm talking about actually updating all the variables at one time. Right? If you want to actually build a Metropolis Hastings proposal for the probabilistic program, you need to build a proposal distribution for all of the random variables at once. So I've already told you Metropolis within Gibbs. That's one way to set up such a queue. Indeed, that's true. But what if you want to do better than that?
Sorry, I have a question.
Yep.
So if you don't know about the graphical model, how can we propose a distribution that fits the graphical model? This
is a good question. It's actually that you're getting to the main point, which is you can propose all of them at the same time, but the chances of that being accepted are vanishingly small, like unbelievably vanishingly small. In the case of the graphical model based proposal like this, the joint probability of the joint proposal will change because of the guard expressions and the link functions for the observes. So the probability of one set of sampled values for all the latent variables compared to the set of sampled values for the proposal could be wildly different because you're going to be changing branches without knowing it. So you're going to get a valid execution no matter what, but the values will be the values of the joint distribution will be very, very different from one sample to the other. So it's not going to be very efficient. But okay, here's some mechanisms. I shouldn't belabor this point too much because we really need to get to BBVI. So there's one thing there's another thing that you can do, and it's like kind of dumb, but like it will give you a sense of how one can do this in the evaluation-based case, right? So we can start with a simplified version of the algorithm. So we just we define Q of x prime, which is to say the random variables on a particular trace, to be just the joint like the prior probability of an execution, right? In other words, at each step of the MH algorithm, we just sample x prime from the program prior, which is independent of the previous sample, right? And we know that we can generate these samples by running the program. And now the acceptance ratio for generating samples from the program simplifies, right? Because we can just now write down what these are, right? So we've got the likelihood times the prior of the newly generated trace times the proposal probability. This is the proposal probability down here, and the likelihood of the old, the joint probability of the old trace. These two terms cancel, and all you're left with is a ratio of likelihoods. Okay? In other words, you run the program once, you are on one trace, you're in one part of the control flow. You run the program again, you go down another control flow, you evaluate the ratio of likelihoods, right? And you either decide to stay on the control flow path that you were on before and at the old sample value, or you move to the new control flow path. Okay. So when we propose from the prior, the acceptance ratio is the ratio of the likelihoods, and our likelihood, blah, blah, blah. We know how to compute the likelihood because we know how to do this from the likelihood weighting algorithm. So we can use the evaluator that we've been talking about, and we just evaluate the acceptance ratio as the ratio of weights, and we're done. But the mechanics of sampling are really, really different, right? Because you're on a trace, you're on a control flow path, you run the program again, you get another trace, you compare their joint probabilities, and you decide to move from one trace to the other. So you're in the graphical model, but really what you should be thinking about is the control flow path of the program, and you're actually moving around the control flow path of the program according to this MH rule.
Can I ask a question about the path again? So you just said something like the trace has a probability associated with it.
Mm-hmm.
How?
Mm-hmm.
Like, is the probability, so like, because the way that I understood was that the trace is like the path you take.
The trace has a probability associated to it.
So it's the path you take, and then where you end up, the probability at the spot you end up, or?
No, it's technically the trace probability is, you would also in here, like to compute the trace probability using the evaluation-based inference engine, you would also put here sigma of log W plus log prob D. I guess we need to put a temporary variable here. So let's say X is sample D, log prob XD, and then return X sigma. So that would change this line into these. So the trace probability is record the probability of all the samples, record the probability of all the observes, and now we have the trace probability. We have the joint probability of a trace, which, by the way, is the same as the joint probability of a configuration of variables, right? The only difference is now that when we sample X in this evaluation-based way, we are going to go down different control flow paths. Because these if guards, again, like these guys right here, they're conditional, like which way you go is conditioned on the values that you sample. Now, what I'm saying here is that the dumbest way to do a trace-based Metropolis-Hastings algorithm is to propose from the prior, which means that in the acceptance ratio for the Metropolis-Hastings algorithm, all of the prior terms cancel, so you don't even have to record them. So you can actually use the exact same evaluator you had already, and you just run the program once, look at the weight, run the program again, look at the weight, and you compute the ratio of those two weights, and you decide to move to the new trace or not, depending on the ratio of those likelihoods, the weights that you've accumulated. But we're about to make it much more interesting.
Can I ask quickly? When you say like move to the new trace, I think what you're saying is that we want to like keep the sample from that trace. Is that what you mean?
Yeah. So I mean, it's just exactly what you expect. So if you do independent MH, right? So this, as in algorithm 7, is the important sampling importance likelihood weighting evaluator, right? And independent MH says, set the log weight to something, evaluate the program first, get the log weight out from evaluating the program. That should be sigma of log W. I realize there's more errata. That's fine. And then for for the number of sweeps, you reevaluate the program. You simply propose from the prior. You reevaluate the program. You get the log weight out of having evaluated it under your likelihood weighting evaluator. You look at the ratio of those. Really, this also errata should be exp of these. I'm finding lots of errata in these. That's great. And then you do the Metropolis Hastings thing, where you just decide whether to so basically you decide to stay or go depending on the acceptance ratio of so yeah, if blah blah blah, then if U is this is acceptance ratio. So if U is less than alpha, a uniform continuous quantity, then you go. Otherwise, you just stay, right? Mm-hmm. Okay, so that's all that's going on here. But we're going to make it more fun in just a second. Everybody ready for the more fun version?
Can I ask one last question?
Yes, please. Absolutely.
Is this in any way better than importance sampling? Because it seems like you're sort of doing the same thing, right? But throwing away the samples that have low weight.
So this is actually kind of an interesting thing, and it led to a couple of very interesting pieces of work, which is to say that if you have a sequence of weighted samples, you can transform them into this representation using exactly this trick, basically. So you can either build an unweighted sequence of samples from a weighted sequence of samples by thinking about it this way. And that's kind of a neat little trick, which we've used in a couple of ways of doing online streaming compression of data and all sorts of crazy trickery.
And you could do it after the fact, right? You could just look at the sort of trace of weights and then say this one wasn't accepted, this one wasn't accepted, and just throw those samples out. Is that right?
You can do all sorts of fun things. Yeah, there's lots of ways to transform weighted samples to unweighted samples using this reasoning. Exactly. Yeah. Okay. Cool. So this is silly because it's the same as importance sampling. And in fact, we know that it's less efficient statistically because we're literally throwing away computational effort. And this is how you can see why raw equalization and keeping weights around and doing weighted expectations is actually computationally more efficient always. But there are things that you can do. You can basically make more intelligent proposals, right? And these are the gateway drug to crazy Metropolis Hastings algorithms for probabilistic programming systems. So great. So I guess it's Wingate and David Wingate that has the original paper on random database Metropolis Hastings, also called lightweight Metropolis Hastings. And what you'd like to be able to do is modify in the evaluation-based inference setup a single or subsets of variables at a time, basically to get better mixing. And to actually condition on where you are instead of doing an independent Metropolis Hastings. Independent Metropolis Hastings hides some challenges, right? So in particular, you don't have to deal with traces with different support and lazy evaluation and that sort of stuff. So here's LMH pseudocode. It's kind of fun, and we'll go through how this works. So let's pick some variable. So we're going to talk about, this is basically, we're talking about Q now, okay? We're going to pick some random variable in the domain of the trace. So the domain here, X, cal X is a map from random variable names slash addresses to values, right? And then we construct a proposal X prime, P prime, and P prime is a map from random variable names slash addresses to log probabilities of the corresponding sample value by rerunning the program, okay? But we're going to rerun the program in a very particular way. For expressions, sample D with variable X, if the variable that we're sampling is the variable that we picked, X naught, or the variable that we're sampling under this expression is not in the map of random variable names, it's not in the domain of that map, then we actually sample its value from the distribution and shove it in a new map. Otherwise, we actually reuse whatever was in the map to begin with. Okay. And then we shove in the probability map, the probability under the distribution that we sampled the new value of X from, the value that we've stored for X. And then for expressions observed DC with variable Y, you always calculate the probability under the distribution of the encountered value. Okay. So this has got a weird acceptance ratio now, and this is where spending a lot of time doing Metropolis Hastings and sampling would be helpful, but we'll try to get as much of it in as we can here. So the acceptance ratio is always the joint of the proposal trace over the joint of the starting trace, and then we have the Hastings ratio, where the Hastings ratio now has to actually compute what we just talked about in this procedure, where we pick one of the random variables in the trace. This is X naught. And then we construct well, I guess actually it's better to do it, look at it down here. We pick a variable from the trace X naught, and then we construct a new trace conditioned on the old trace and X naught, ignoring the observations. Right. The reverse ratio, which I should have done, the reverse ratio is pick the same variable X naught from a different trace, X prime, the trace that we moved to, and then specifically go exactly back to the old trace given where you were. So basically this construct is a new way of thinking about Metropolis Hastings proposals and constructing Metropolis Hastings proposals that are by design reversible. So long as you can do the computation to compute the Hastings ratio, you're okay. So in other words, you have to design a proposal such that it's reversible and you can compute both directions, okay? So the first thing is the ratio of the choice of X naught, a particular random variable in the trace for two different traces. Well, that accounts for the relative probability of choosing that particular site. Right? And even in the FOPPL, different traces can have different lengths. Right? If you go down loop expressions that have sampling on one side and determinism on the other side or something like that, you can have traces with different numbers of samples in those traces. Okay? So the probability of choosing an initial site, a site to change, is exactly the ratio of the lengths of the traces. The original trace is of length big X, and the proposed trace is of length big X prime. Okay, so we've got two different trace lengths, and then we have to deal with effectively computing these ratios. And I'll hustle through this a little bit because I want to get to BBVI. And you don't have to actually implement this, although it's super fun to implement and super cool, and it's like the whole point of keeping around state. So we can express the ratio. So we're going to look at the probability, where basically we're going to look at this first term right here. Okay, this is the proposal going to x prime from x over the new joint probability of the new trace. So what's the joint probability of the new trace? Well, it's exactly what you would expect. It breaks down, and in our case, it's just the product of all of the likelihoods of the observes times the product of all the likelihoods of the sampled values in the new trace. Okay. And just to be clear, x prime is the domain of this map that we have, and y prime is the domain of the probabilities, taking out the sampled random variables. So joint probability is easy. The proposal probability, this is where it gets fun. Compute the probability of the proposal, the proposed new trace. We decompose the set of variables x prime, right? This is the new trace, into those which are sampled and reused. So in other words, there are going to be some that are the same as the old trace, and there are going to be some that we sampled. And it's going to depend on how we go through the control flow path, whether or not they're sampled or reused. So based on the rules that we set out on like 2 slides ago, the set of sampled variables is, well, we resample the site that we choose to resample, union all of those variables that appear in the trace, the new trace, that were not in the old trace. That's what this is, right? But we know that all of these newly sampled values were sampled from the program prior, so the proposal probability is just the product over all of the variables that were sampled when from the prior when creating the new trace. Okay. Cool. Well, some of the terms in the prior and the proposal cancel, right? The ratio of the joint relative to this proposal simplifies, right? So it only has the likelihood terms that come from the joint. And then we know that the prior is the product of, x probability of the x prime sampled variables and probability of the x prime reused samples. And this one is just the sampled. So all that's left is the probability of the reused variables, okay? All right. So that basically, when we're looking at this ratio, says that this ratio for LMH, so we're going to pick a site according to the length of the traces, and then we can evaluate this ratio by, in our lovely interpreter, evaluating the likelihood on the next path and evaluating the probability of all the sampled values, all the reused values in the trace. Okay. Now we can look in the other direction. And basically, yeah.
Sorry, what are reused variables?
So this described how let's see, this described how the variables, where did we do it? Here. So when we're running, this is LMH in pseudocode. So when we hit a sample statement while we're running our sampler, we've chosen, we're proposing some new site, and we make a change to that site and anything else where this holds, right? So when we rerun, we hit x naught, and we definitely sample a new value for x naught. But if that puts us on a new control flow path somewhere else in the program, then we can encounter new random variables that are not in the domain of the map of random variables that we have. In other words, they're not on the current trace, right? When that happens, we have to sample a value. Otherwise, we know that the control flow has gone back onto the same path as the original path, and we just reuse the variables. We reuse the values of the random variables. Okay? So that's reused versus sampled, right? And we've just done the joint probability. And great. So now we have some stuff that cancels. The inverse is exactly the same, but the reused variables are exactly the same in both traces. So the final ratio is fairly entertaining. Where you compute the basically you can run a lightweight Metropolis Hastings algorithm. You can run a trace-based Metropolis Hastings algorithm by picking a site, right, according to this probability, 1 over that probability, right? And then computing as you go all of the likelihoods and keeping track of which variables are reused or not reused. And summing or not summing the correct probabilities in order to compute this ratio. And you accept or reject the changes, the new sample based on this ratio. Now, why are we talking about this or whatever? This now is kind of an alternative version of Gibbs sampling that pays attention to the control flow of the program, right? You're picking a site, you make a change to it. Then you evaluate this ratio and you decide whether or not to go. It's a different version of MH within Gibbs, and this it turns out to be pretty efficient, actually. More to the point, this approach works in the higher order probabilistic programming language setup. And even more to the point, when you have access to continuations, which we'll talk about, I think, in the next lecture, there can be extremely computationally efficient versions of this, which is to say that the way I've talked about this, I've said rerun the program until you hit a particular random variable, change that random variable and keep going. If there's a way that you can just start the program execution at that site, which there are ways to do that using programming languages techniques, then you can avoid re-executing huge sections of the program. Okay, I'm running out of time, so no pause here. Okay, pause here. 3 minutes to eat. Go. Awesome. So in the preceding, I brushed over something that is an important detail, and it's very important when we start talking about higher order probabilistic programming languages and evaluation-based inference in those, which is that I sort of, in these preceding slides, said things like, where is it? This is a map from random variable names / addresses to values, right? And nobody called me on it, which is pretty standard. Just little tricks that we can do to get around putting stuff out there straight away. But in the first order probabilistic programming language setting, we can basically conflate the idea of variable names and addresses, whatever addresses are, because in the process of compilation, we identify every single random variable, and they're gen-simmed, and they correspond to nodes in a graphical model, right? In other words, we give them names, right? So in evaluation-based inference, we don't have a name for a random variable. So in order to construct such a map, we have to actually be able to name those variables, right? So that we have a unique name as we're, shooting traces into the control flow graph of through the control flow of the program. So this name, the way to name random variables, is known as an address. The key desiderata for addresses is that they uniquely and reliably identify random variables. In other words, if you encounter the exact same random variable, it should be given the same name, right? That's it. And no two random variables should be given the same name. So addresses can be constructed dynamically at runtime. This is what we do in the higher order probabilistic programming language. But to give a flavor of what this entails, and this is important to sort of think about, we can write a FOPPL source code transformer that assigns a unique address to be consumed. Okay. So now we're back to source code transformation in the style of the compiler. And basically, you don't have to pay attention to any of these rules at all. All they say is go down and do a source code transformation. And when you hit a sample statement under an addressing transform, make a name and insert it in the sample statement as a first argument. So really, we should rewrite this as like sample star and observe star. So in other words, we're going to actually change the definition of sample and observe to take a name. And we can do this via a program transformation, in other words, a source-to-source transpilation, which effectively says put new address in each sample and observe statement. The reason for putting this in front of you right now is that I believe that I'm going to make it so that you don't actually have to know about these addresses. But for those of you who end up doing some sort of inference compilation for higher order probabilistic programming languages, or do variational inference in Pyro or something like that for your project, you will see that there are addresses that are names that identify random variables. Okay, so in the FOPPL land, those names correspond to literally the graphical models and the variable names that we have in our that we generate while we're compiling. But we can also transform the source code for evaluation such that when we hit a sample statement, we have a unique name for that variable. Okay. This is what we need to get to. This is going to be fun. 20 minutes for black box variational inference. Should be fine, right, Brad? Yeah. Okay. We will actually cover variational inference writ large. If you're unfamiliar with variational inference, I'll probably give a lecture on variational inference, but we just need to get this thing out in front of you right now, and you'll think about it, because it's, again, homework 4, and we need to get a move on so we get the material into you. So we've considered basically sample-based inference algorithms solely so far. We could also think about enumeration-based inference algorithms, which we are not going to consider because they don't work in continuous valued spaces. And we could think about belief propagation-based inference algorithms if we transformed the probabilistic programs to factor graphs. Those do work, but generally speaking, don't have the same kind of guarantees. Another way of approaching inference is to change the inference problem from one of sampling into one of optimization. And this is where at least half of the class should have their ears go, ooh, pick up and say, I know something about optimization, so what do we do? So how do we transform an inference problem from a sampling problem into an inference problem? Well, the key thing that one does is you learn the parameters of a distribution in a way that the parameterized distribution learns to be close to the posterior distribution of interest. And in some sense, it's the easiest idea in the world, and it's, that idea is variational inference. Black box variational inference is what we'll talk about right now. which is compatible with probabilistic programming in a very, very nice way, and doesn't even require automatic differentiation, although you're likely to implement it using the tools of automatic differentiation instead of the way we talk about it here necessarily, but you'll see. So what's the goal? What we want to do is we want to learn an approximation to the posterior by maximizing a thing that we'll refer to repeatedly throughout the course as the evidence lower bound. Okay, so the critical thing is this little thing right here. If you understand, this is variational inference. It's variational inference in 2 lines. Okay, so what's going on? This thing is the elbow. That's what we call the elbow, and it is an expectation over some distribution Q, which we've never talked about. Okay, but this is going to be the inference artifact. Instead of sampling based, we're going to learn this thing Q. That's our target. That's what we want to learn. And what is it? It's the expectation over Q, which is parameterized by some parameter lambda. So these are going to be the parameters of our variational distribution Q of this quantity, the log joint. So this is y and x that we've been talking about. So the y's are the observed, x are the latent variables in our program, divided by the probability of the latent variables x under this variational distribution Q. Okay, and really, in a nutshell, if you write this out, which is pretty straightforward, right? If you decompose the log P of x given y, if you decompose the joint distribution in this way, then you'll see that the log P of y is constant. There's no x term in it, so the expectation, it comes out of the expectation. And just shows up as log P of y. And what's left is in exactly the form of the negative KL divergence between this distribution Q and P of x given y. And if there's anything you know about KL distributions, or I hope you know about KL distributions, is that there are 2 things you need to know. Like when KL gets small, the 2 distributions in the divergence are closer, and when KL is 0, they're exactly equal. Okay, and KL is positive. Okay, Kullback-Leibler. Okay, so DKL is positive, goes to 0 when Q equals P, or when Q goes to P, okay, so on and so forth.
Why sorry, I have a question.
Yeah.
How do you decompose P of yx, joint probability?
How did I decompose it? Right here.
Yeah, because you have green and I'm not seeing it. The first name is P of x. Ah, okay. Okay. Thank you.
Yeah, great. Sorry, I should switch color. Yeah, I don't know why I stuck with that color. So the point is, because this is a positive number, then this term, this elbow, is a lower bound on the marginal probability, right? Which means that if we can maximize this thing, maximize the elbow, then that's equivalent to, because log P of y is fixed, we don't need to know what the value of log P of y is, it's just fixed. It's equivalent, maximizing this is equivalent to driving this KL to 0. I've just explained variational inference to you somewhat effectively in 4 minutes. Whether you remember it or not, doesn't matter. We'll get to it, you'll remember it later, but that's the essence of variational inference, okay? This is fixed. Log P of y is fixed. The elbow is a lower bound that involves a KL that has as part of it a KL divergence between your variational distribution and the posterior of interest. When you drive the elbow up and make it as close to this fixed evidence as possible, the KL goes down, being driven to 0. ideally.
What are we maximizing over, like with respect to again? Is it X, lambda?
Lambda.
Okay, thanks.
Yeah. Yeah. Great. So the point is that doing this, right, makes Q close to the posterior in the KL sense. And there are other versions. You can do different F divergences, alpha divergences, total variation. There's all sorts of ways of setting this up, but we're going to just talk about KL divergences here, Koldeback-Leibler divergences, right? And further, and this is where we start to talk about where the black box stuff starts to come in. If we say that our variational distribution, Q of big X parameterized by lambda, is what's known as a mean field approximating family, which is to say that it decomposes as a product over some other Qs. The choice of what the distribution type is free. Each of them is going to have some associated parameter. So you really should think about this as a vector of parameters, and this is obviously a vector or structured set of latent variables, and our family is going to be this product family. Okay, so in other words, we're not going to be able to. So we're treating in the approximate posterior all the variables as if they're independent in the posterior, which is of course not true, right? But we're gonna find the closest member of this family to the true posterior. So like, what's the closest uncorrelated distribution to the correlated posterior that we can find? So the fun thing is that we can do gradient optimization now. So our inference problem has turned into, we're not inference anymore. We're doing optimization, and we can do gradient-based optimization of this objective. So our objective here is some empirical estimate of the elbow as a parameter of lambda, and you can do SGD with a Robinson row sequence and of step sizes, and we now have convergence. So we're done. Okay. So we're going to basically just think gradient descent on lambda with reasonable step sizes. What BBVI does is it uses what we'll call a reinforced style estimator. Okay, so what we're after is we want the gradient of this expectation under Q of R of X lambda. So R of X lambda, I'll just define down here. It's totally fine. It's just if we plug this in, that's the elbow. But the reason for this is just to keep this expression a little bit more simple. So the expectation over Q is an integral over the domain of the random variables in your program, right? Under reasonable conditions, you can pass the gradient inside the integral sign, and then you can do what is this chain rule, right? So you've got the gradient of Q times R, then Q times the gradient of R. Fine. Cool. Awesome. Now, we're getting somewhere. If you, yeah, I mean, I've already said that we've got the elbows there with the substitution. So the critical part is that this bit right here is 0. This is, yeah, I mean, we can see this. The expectation over Q of grad of this ratio R is just the grad lambda log of the ratio. The top term doesn't have lambda in it, so it goes away. That's totally fine. So this is just the negative because of we'll take the log the log reciprocal of the gradient of the expectation of the Q of the gradient of log Q. Then this is just the integral over Q of grad log Q. Fine. And we can now yeah, so this uses the d log ddx log x is 1 over x trick here, so on and so forth. And we're running out of time, which just makes me uncomfortable, so we'll have to go through this a little bit more slowly, but we'll come back to it in just a second. The point is that this is just the gradient of Q when you rearrange the log rule, and then you pull the gradient out, and this is just the gradient of 1. So this term goes to 0, and you can do that on your own if you want to. Awesome. This is the identity that I just used. You just rearrange that identity. So if you also use that identity on this side, this is in the book, but we'll go through it again more slowly in just a second once we get through it. If you use that identity on this side, in other words, the gradient of Q, if you use this identity here and you substitute in Q log Q, right? Then this side, this expression here, turns into this EQ grad log Q of the ratio, and you can stick a constant in here. Okay. Fine. So there's some algebra which we should do more slowly, and I should do it on the board. Is probably what I should do. The point is that we can transform an inference problem into an optimization problem by forming a variational objective, which is to maximize the elbow with respect to some variational parameters. That's what we did here. We can select some approximating family. We'll choose a mean field family. That's totally fine. If you just do chain rule and use this identity, which is just the relates the gradient of log Q to 1 over Q and the gradient of the inside, so you can rearrange this in multiple ways, right? I mean, that should be obvious. You can take this and you can move it over here as 1 over. So you use the chain rule and that, and what you get at the end of the day is an estimator for the gradient, which can be expressed, an estimator for the gradient of the elbow, which can be expressed as an expectation over your variational distribution of the gradient of the log of your variational distribution times a ratio where you can compute all the terms by construction. So this is the joint distribution under the program. You know how to compute the joint distribution at this point for sure, and you have a free choice of Q, so it would be very strange to choose a Q in which you couldn't evaluate this. So you want to choose a Q that you can evaluate this, and moreover, you will want to choose a Q or a set of Qs in which you can compute the gradient of the likelihood of the latent variable X under the model parameters, under the variational distribution parameters. Okay. Which you can do for basically all distributions. including discrete distributions. So long as you can sample from your variational distribution and you can compute this ratio, which you should be able to do, then you have an estimator for the gradient of your variational approximation of the Monte Carlo form of just average over samples from from your variational distribution, summing, averaging the gradient of your variational approximation times the log ratio plus a control variate, and I'm not going to talk about the control variates. Okay. So the BBVI evaluator, and this is now starting to get cool and very close to state-of-the-art stuff, right? So you now need to be able to run your program not from the prior, but from a variational proposal kernel. So in other words, you're going to, for every random variable in your program, all of the addressed random variables in your program, you're going to have a queue, some variational family for that variable, that address. When you evaluate the program, you sample from these queues, not from the P's in the program, right? When you run the program, you evaluate and track in your state the joint distribution of the samples that you generate under the program and the probability of the samples that you generate under your proposal. And while you're going, at the end of the day, or however you however you want, at the end of the day, you have this expression for the overall gradient, right? Which, of course, if you have a mean field approximation, clearly breaks down because the log of Q of all the random variables is going to break up into the sum of the logs of the individual random variables, and you just have the weights as defined. So long as you can take a gradient or have a set of you basically must also have a gradient with respect to parameters implementation for each variational kernel proposal. This does not require automatic differentiation support in the implementing language, so you can actually do black box variational inference provided that you have a library of variational distributions for different variable types, and you have a library that contains the gradient with respect to parameters implementation for each of those, right? Of course, you can use you can use automatic differentiation if you want to get the gradient of a likelihood expression for each of these variational approximations, variational distributions with respect to its parameters, given the sample values, if you want, but it's not necessary. So that's it. So we talked a lot about evaluation-based inference, yep. And now we've got LMH, which you don't need, you don't have to implement, but you should think about. And now we've done black box variational inference very quickly, but with enough detail that you should be able to go read the book and figure out what's going on now and implement it. But yeah, so ask questions on time.
What do you mean by type of variables? In different distributions, or? So
this is a really good question. So I specifically use type rather than distribution of the random variable because type in the, well, it depends on the type system that you use, but really what you need is for the Q for any particular random variable to have the same support as the prior. So in other words, in the original program, X might be governed by a normal distribution, but in the variational family, you might choose the variational family to be a mixture of normals or to be a normalizing flow, if you're familiar with normalizing flows or something like that, that has the same support. If it's uniform 0-1, then you could make the variational distribution a mixture of betas or something like that, or a variational flow constrained to the 0-1 space or something like that. So the distribution type in the prior in the variational family need not be the same, but the support has to be the same.
What do you mean by kernel here?
Variational proposal kernel, what we mean is basically, remember a Q of X given lambda, we make a mean field assumption. So X I guess, given lambda Xi. Kernel is probably a bad word to use here. We should just proposal distribution kernel instance, whatever. You can think of it as a kernel because you like in the RBF kernel kind of sense or whatever. There's just some notion of closeness. It's just a distribution. I should just really each variational proposal distribution. A kernel is a bad word to use there, probably. Yeah.
I have another question about the trace.
Okay, good. All right, we'll go back to traces. I'm hoping for a little bit of a conversation about this so that you're, I'm doing a thing that all of my students will know is, or I'm pushing you forward, way forward, and we'll come back and we'll make sure that this is okay. But yeah, go ahead. Question about the trace. Go for it.
So a trace is, it's like a list or a vector, and because it has a length.
I would think of it as a set or a hash map that goes from addresses or random variable names to their values.
Okay, and it adds a new pair every time it goes to somewhere new in your program.
Every time you encounter a sample or observe statement, you add something to this set hash map. Yeah.
Okay, at every single sample observed statement, but nowhere else.
Correct.
Okay.
Because the control flow and the traditional programming language's notion of trace, which is this set of all intermediate computations. So Mia talked about single static assignment, I think. Did you talk about that before? Right. So you can do transformations of programs into forms where you represent every single intermediate value. This is also known as a Wingert list when we talk about automatic differentiation. You'll see another thing of this in the next couple of lectures when we just chillax and do some stuff that you don't need to implement, but talk about it instead. A trace is that sequence of intermediate values.
Okay.
And the functions that generate those values. So in our particular case, it's the sequence, and you really do need to keep track of the distribution type in general, like the actual type of the distribution.
Okay. And is it related to, like, when you get an error code, it shows a stack trace? Similar sort of definition for trace. It's like a map of where you go.
So the stack, like where you are in a program, is more like the address.
Okay.
The trace is, again, you can think of the trace as the sequence of growing bindings in the environment. So in other words, like you have the heap, and that is a sequence of values that you've generated and stored during the execution of the program. That's part of it because there's also transient stuff on the stack that you compute on the way, right? So it's like you can think of the trace. You can think of a trace as a snapshot of the entire computation as you go, leading up to a collection of all the values ever generated, including all the intermediate computation steps. But in our case, when we're doing inference, we don't care about the deterministic steps because the trace, we like to say that the computational trace is deterministic given all the stochastic elements. So we can characterize a unique trace by the values chosen for all the random variables.
Okay.
Vasilios, the answer to your question is B is a baseline in reinforce. Yes.
I want to tag on to Emma's question. In some sense, like intuitively, maybe, well, the fact that the order in which variables are sampled does not seem to matter because you're sort of defining it as a hash map, right? Like, is that just have to do with the fact that probability like a joint distribution can just be, how do you say that, factoring two probability factors is.
The order very much does matter, but that's why this addressing thing, right? So the program must go through a sequence, like the map of traces is the finite state automata that describes which address or which random variable you can generate next from wherever you were, from the values of the current trace, right? So the order very, very much matters, but the fact that you can identify each random variable in the FOPPL context simply by a name means that you can, by virtue of the fact that your trace has a random variable of a particular name, you can go back and deduce that you went down a particular control flow path.
Yeah, so the order in this sense is defined by the program, not by, and it's unnecessary to redefine it in the map or in the trace.
And for you, when we start talking about, and for anybody who cares about it, when we start talking about, and we probably won't even touch this in this class, when we start talking about learning surrogate models, which is to say replacements for the generative model that maintain the control flow, then actually the address succession graph is very, very important.
Mm-hmm.
So you can under approximate a probabilistic program by learning a surrogate for the address transition, like learning a generative model for the address transitions. I think my screen share just went away. So ask more questions. I know there are more questions, especially on this last part. It was super fast.
Yeah, so with regards to mean field assumption, are we doing it just to have easy computation of the gradient procedure?
Yeah, so yeah, exactly. So in this particular case, when we talk about black box variational inference, the whole point, it's actually, I give Dave Bly a really hard time about this, and I may or may not go through one of his lectures on variational inference. So there's a subtle distinction between automatic differentiation variational inference and black box variational inference. So there's nothing at all, if you look at this expression right here, to keep you from using a more expressive family for Q. You can use some crazily complicated family for Q, but that will come at the cost of requiring you to have an automatic differentiation system, maybe not the worst thing in the world, but also having Q be able to express the structure of the program, which is not so bad in the FOPPL case, but it's really, really hard in the HOPPL case, as we'll try to get to, and maybe, get you all interested in.
So just to make sure that it's easier if you have like mean field assumption?
So the mean field assumption means that it means that, where is it? Yeah, it means that this is true. This is the only requirement that you have. Whatever variational distributions you have in your distribution library, you only need the gradient of those with respect to their parameters, because this thing factorizes in the mean field sense. But if you have dependencies, then you have to be able to pass your gradients through the entire, like this thing has to be differentiable with respect to all of its parameters, right?
Okay. So like in HOPPL case, if like number of random variables in the program kind of grows, then these dependencies, yeah, would make it complicated.
So it turns out that you
compute
can do,
gradients,
and
right?
there's a paper by David Wingate and Theo Weber. Wingate is a professor in Utah, and Theo Weber is a research scientist at Google DeepMind, where they do black box variational inference for higher order languages, and they just do it, and literally nobody knows whether or not it's correct. It seems to work, but in terms of like proving the correctness of the algorithm, nobody knows.
Okay.
So how do you do it? Like do you just make up, because you don't know for every evaluation of the program, you don't know what distributions you're going to encounter, right? Like
So you keep a lazy map, and every time you encounter a new address, in other words, a different uniquely identified random variable that you've never seen before, you lazily instantiate a variational distribution for it.
You just add a new queue and you just do it as you need them.
And when you compute the gradient, right? Well, there's not going to be any gradient terms. Like there's going to be no information about that particular yeah, I mean, yeah, it just works out, basically. It seems to. Nobody knows for sure. The algorithm has been proposed. So, Baron, you want to give some, I guess you're about through implementing this, right?
Yeah, somewhat. Like, can you finish your
I just wanted to,
request?
Wanted you to share your experience so far.
I think so far it's been pretty straightforward. What can I say about this? Yeah, I think like just, the infrastructure that you need in the homework 3 should be enough to implement this relatively easily. I will say that I haven't done the control variates yet, so I haven't done that B hat. But that's what I thought. So, but I haven't tested it yet. The other thing that I'm running into now is just that you're so if you take values for example, a Gaussian distribution, like your sigma cannot be negative, right? So that's some just a practical thing that I just ran into. That's something to maybe think about how you would solve that. Other than that, I don't think I have that much to say about it.
Yep. Sorry to put you on the spot.
That's fine.
The critical part for now is that this bit right here makes sense. The rest of it is algebra that you can do, and you can look in the book. But the point that we've transitioned from a sample-based representation of the posterior distribution to an artifact, which will consist of a library of variational distributions whose parameters are fit via an optimization procedure, means that your inference algorithm will behave incredibly differently, right? When you run inference, what it means is you will solve an optimization problem to build a variational approximation to the posterior, and then you will evaluate the program under that variational approximation distribution only, and then compute return values for the samples from this variational approximation. Right. So it's a very different kind of thing, but it actually turns out that it's a very different kind of thing. I'll just leave it at that and not confuse you by thinking too far ahead. But we've been doing these asymptotic ergodic kind of sampling procedures. We talked about LMH today. I should have just skipped it and just done black box variational inference more slowly, but well, next year. We've got Hamiltonian Monte Carlo and importance sampling, all these things. They reevaluate the program, reevaluate the program, reevaluate the program, and eventually they equilibrate, right? This says you can't do anything. You get zero information, you get no samples, and you get nothing until you solve an optimization problem. Once you have an optimization problem, then you can generate a very, very high quality set of samples quickly. And that's kind of interesting to think about, right?
Maybe I can add something now that you said all this. Is that I actually, when implementing this, I found that in some sense much more intuitive what comes out of it than the earlier things. So the earlier things, you just get samples, right? And here you actually get some idea of what this thing should be, which is like a distribution. In this case, it's an approximation to that distribution. But for the simple cases, this is it's easy to read into. Like you can literally read off the parameters of these queues.
I have a question about independent MH.
Yeah.
Could we choose, is there an issue of choosing a trace with very high likelihood such that all subsequent samples or traces are rejected?
So this is a lovely question, and it's true also of importance sampling. So you can think about like is this a good thing or a bad thing, right? It may be that there is some trace, but think about, we're still working on this. We'll see where Berend is on the construction of this thing. I'm pushing it pretty hard, but think about a reinforcement learning task, if you know anything about reinforcement learning, or think about a pinhole problem. Like literally only one setting of the random variables gives you high probability. The rest of them give you all very, very low probability. That may be a good thing, provided that you can find it. In other words, you should have a high likelihood and you should never ever mix off of it. All right. The fun thing is that all of these have asymptotic convergence guarantees, right? So even if it's, orders of magnitude more likely, right? If you run this infinitely long, you will mix off of it. Right? Because it's Metropolis Hastings.
Sort of explains it, but I'm just wondering if you land at some kind of optimal point.
Yes, you can get stuck. You cannot mix over modes. You cannot. Yes, okay. Of course. All in finite time. Yeah, you can get really screwed. Yeah.
Okay.
Even worse, you can. If you don't have a valid. If it can be very difficult, particularly if you program things that look like rejection sampling, it can be very difficult to find initializations of your sample space that do not have negative infinity log probability. In which case, you can just generate garbage samples for an unboundedly, not an unbounded, but for unbounded. Yeah, I mean, it depends. This is like size of infinity battle, right? It's like an unboundedly long period of time before you actually jump onto a valid sample and then stay there forever, right? Yes. Yes to the above. You can wander around in the wilderness for a long time, or you can find the mountaintop and stay there, even though there's another mountaintop over here that's slightly higher, and you can't get. Yes, this is true of Metropolis Hastings in general, and the whole point of these different exercises and thinking about different general purpose Markov chain Monte Carlo algorithms is that sometimes, and you'll start to see this when you start solving the HMM problem, right? There's an HMM problem in the homework, and it's meant to make you think about how you mix over such spaces. If you make changes to one random variable at a time, it's actually impossible for the chain to mix. So you want to have proposals that allow you to move more than one random variable at a time, right? Which means that you need some proposal mechanism. You can think about basically what this lightweight Metropolis Hastings algorithm is doing is looking at the trace, picking somewhere, and changing the execution from that point forward, all of it. So there's a joint proposal that satisfies the program that's dependent on one, but reuses as much of the randomness as possible. So you basically are dynamically choosing your the number of random variables that you're changing at once, which means you're making a correlated proposal, which means that it will mix pretty rapidly. Actually, it works really, really well. If that makes any sense at all, based on what we went over today. Yeah.
Yeah, that makes sense. Thank you.
Yeah.
I don't know if this is related, but I have like a memory, but I can't remember exactly what we said now. Didn't we make some assumptions about like the function being absolutely continuous? Or I have like some memory of us talking about that. Is that related?
Do you?
Do we have it in the slides?
I don't think so.
Okay,
but,
I'm just imagining it.
Yeah. Nina, you haven't said a thing today.
I don't know what to ask.
Oh no! Oh no! It's the Naomi comment. No. Namrata, Mia, Ryan said something. Amin said something, which was nice. Thank you. Appreciate it. Nice to hear a new voice. Vasilios, you've been quiet as always. But you asked something in the chat, so.
If there aren't any like material related questions, I want to revisit the question of the due date of the assignment. I don't know if that's like, I mean, you seem pretty set on Tuesday, but.
Yeah, we have to get a move on. Yeah. Otherwise we're just not going to get to the stuff that's actually advanced machine learning and actual probabilistic programming. We're building up a whole arsenal of understanding, but we gotta do it.
So on that, I have a proposition. And you sound thrilled. Because it seems like things are going to come really quick right now. And I know at least I am floundering. And so I was wondering if it's possible to do the homeworks in groups, say starting after homework 3, maybe in the groups that we're going to do our projects in, just so that we don't get as destroyed, possibly. I don't know if this is something people.
So I have said that you should work on the homeworks together.
Yes, but we still have to submit something separate. What I'm saying is like we all collaborate on the same thing. I don't know if that'll make it like faster or not. I haven't fully thought out.
Yeah, no, I think I think really seriously you should be collaborating to the point that literally you know what to write, and the only thing that you need to do is write it so that you get the muscle memory and you really understand, like when you're writing down what you've decided between the bunch of you, literally all of you. You're not going to make me unhappy at all if I see you on Slack literally write this, this is what you need to do, here's my code, But what I want to see at the end of the day is that you actually type it in yourself so that you get the muscle memory, and you while you're typing it, you think while you're doing it. That's all. So
okay.
For academic, like malfeasance purposes, there's basically no way to cheat at this point. Like just talk to each other. That's the whole point, right? Like
I didn't know that was the extent of collaboration that you meant.
Yeah, like really explicitly collaborate, but at the end of the day, make sure you actually type it yourself and run it yourself so that you, like, while you're typing it, you think, oh, what? What's this, right? Oh, okay, I understand. If I wasn't clear about that in the beginning, that's really what I want. I don't want to torture you with the amount of work. And and honestly, based on the work and feedback, there is a difference in terms of like who is like there are some people that are really going fast and some people that are not going super fast, and those people you should be talking. I know it's COVID time and we can't all get together, right? And that sucks. But there's lots of mechanisms for spending time with one another, quality time, pair coding, and then going off and coding yourself, and then whatever, right? Yeah, totally. Please. Now.
One more thing as well is that I think I talked to Christian today, and I think I convinced him to do another office hours before deadline, possibly on Monday. And now that I said it, you can hold him to it. You have my permission.
Also, I tend to work on Saturday, and this Saturday, if people are really like, so another thing, just to be clear, you should, if you did not get particularly high marks on the second homework, you should find somebody's code. You should find somebody and steal their code from homework 2 and build off of that. Understand it and build off of that, because you will get overwhelmed if the homeworks don't build on one another. If you're not complete and have complete mastery of that earlier thing in terms of the code, conceptually you can have it, but if the code isn't quite there, you need to be building, right? And for that matter, Baron can share the solution code, right? It's like whatever for the previous homework. That's not a problem. Baron, what are the statistics of the homework 2 grades? Do you know? Did you release the homework 2 grades?
I did.
Okay.
As far as I know. If I didn't, then it was unintentional. I don't know off the top of my head what the actual statistics are, but I think that like 90% of the people got 45 out of 50 or higher, and somewhere like half got the full marks, somewhere along those lines, something like that. Is that your question?
Yeah, I wanted to figure out if I should be asking for code or.
I think you will know if you should be asking for code. That's basically the and I don't want to. This is we're getting in danger territory again, so I'm going to shut up. But
I think like most points were deducted in homework 2 for just not showing, like not having a full report. As far as I could tell, everybody had a working code. Almost everybody had a working code. But that's not to say that you shouldn't have a look at other people's code and sort of get some inspiration from how they did it. That's really helpful, actually, to, sort of see what other solutions there are.
For sure. And again, we're talking now homework 4, so we're a little bit of we're actually ahead of the game now a little bit on the lecturer side, right? So we've got homework 3 stuff covered, right? Now I've done at least one lecture on homework 4, so there's no excuses related to pushing the homework out because I didn't cover the material fast enough. So it's out there. Now you need to know. You need to go read about it. At the very minimum, and we'll have another. We'll have another lecture on variational inference, and the black box thing will be pretty obvious. And just to throw it out here, the homework 4 sets you up for thinking about interesting projects, and like if we do have a 7th homework, which is possible, the cool stuff about amortized inference and like meta learning and these sorts of things, they all come out of this framework. So homework 4 in some sense is the one that I really want to get you to, but you have to do all the other stuff to really understand what's going on. So
I have a question that I just remembered from the last homework. So the vectors in the code is the standard vector a row vector or a column vector, or does a vector have an orientation?
I'm not sure that, sorry. I'm thinking, I'm slap happy now. I'm tired, as are you. I don't think that we should be talking about orientations of vectors. I'm not sure that's a politically correct term anymore. But I think that you can have whatever all orientations are cool. That's, I think, the most important thing. Whichever orientation you like, go with it.
Okay, because like I don't think it was a problem with my homework, but I made column vector standard because that's the way I think, but it would fail the check tests because the check was with row vectors, but the matrix multiplication didn't make sense to me if it was a row vector with a matrix, because like that doesn't work.
So I actually remember reading this in your report, and I thought I made a comment. Did I make a comment about it, or like
maybe you did? Maybe I just forgot. I don't know.
So like I'm not sure I understand how you can make a row or column vector in PyTorch unless you go to like a two-dimensional representation, right? You can have a
I might have gone to a two-dimensional representation, then I'm not really sure.
Right. Well, I would say then, if at least as far as I know, if you just have like a 1D vector, it should just be a 1D vector. I don't think there's a notion of column versus row in that sense.
Okay. I think that answers my question. Thanks.
More fun? Or should we call it quits for today? Thank you all for your time and attention. And I will see you on Tuesday.